god, that's so bad.
It's already recording. Okay, 10.2, using combinations. This chapter actually has a second part. It says use combinations and the binomial theorem, but I'm going to skip that part because I'm more interested in combinations. And so a combination is very similar to a permutation, but it's different in one key way. So whenever we were trying to do, in section 10.1, we learned about permutations. And so we started with only, let's say I have a group of 10 things. It could be people, it could be, desks, classrooms, whatever. And I ask you, how many different ways can I order those 10 things, right? And so each ordering, we called it a permutation. And so we started with that, and if I have 10 things, the number of permutations was 10 factorial. Then I went on to say, okay, what if out of those 10 elements, I only wanted to permute 3 elements? Right, so I would want to pick 3, and I would want to basically find all of the different permutations, but only taken 3 at a time, essentially. And so we came up with the idea of like 10 pick 3, right? And this would tell us all of the different permutations of size 3 if we have 10 elements. Everybody clear what this is telling us, right?
Yeah.
And so we can go a little bit simpler instead of 10 and 3. Let's say we have 5 elements, A, B, C, D, E. And I asked you, what is 5 permute 2? Well, here what we're really asking is how many different permutations of size 2. And so if I wanted to list them out, I would list AB, that's one permutation, but also BA, that's another permutation of size 2, right? And we can keep going. AC, CA, AD, DA.
Can it be AA?
No, because we can't repeat it. DA. AE and EA. Remember that these permutations are all of the different ordering, but I can't repeat it because I only have one A. If I had multiple A's, then I could repeat the A's, and we would have a slightly different equation to figure out how many different permutations I have. But this would keep going on forever, right? Well, not forever, but for a really long time. There's a lot of permutations here. Now, what if I didn't care about the order? What if I just AB and BA? Well, it's just A and also B, right? What if I didn't want to count this twice? What if I only cared about the different combinations of letters that I can get out of these 5?
Oh.
So for example, I only want AB. I don't want BA because for me, because the order doesn't matter, BA is the same as AB. And then I would keep going AC, AD, AE, and then B, I would start with B, but not BA because I already have that. It would be BC, BD, BE, and then CD, CE, and DE, and I would be done.
And how do you know all that? How could you know without doing that?
Right, and that's the question that we've kept asking each other like through this whole week. I don't think you were here, but if you watch the video, that's essentially like, well, I don't want to do all this. I just want to figure out how many different combinations can I get without having to write it out. Because obviously here, I'm already done, and so that's pretty quick. But what if I have much bigger numbers? What if I have like a collection of 52 different elements and I want to pick 4? There's so many different combinations that I can make, and I don't want to have to write it out. But does everybody understand the difference? Oh, and we write this as 5 combine 2. And so this is 5P2 and this is 5C2, and that's the difference between these two. The permutations, they care about the ordering, so every different ordering of the letters will count as one unique permutation. But here, the combinations don't care about the order, and so I want unique combinations of my letters, or whatever I'm...
They see 2 permutations as 1.
Right, these 2 permutations, are essentially 1. Now, if we were picking 3 at a time, we would have a lot of different permutations that would all collapse into 1, which is the example that I have here. And so what I have here is very similar to what we talked about right here. But right here I have, okay, what if I have A, B, C, D, and E, same as before. I have a group of size 5. But 3p5, instead of, I have this in the wrong order, sorry. This should be 5p3, yeah. Let me fix that. But 5p3, let me do it real quick. Five, 3.
Bless you. Thank you. Bless you.
For 1 day of class? I don't think it's worth it. Okay, so in this example I have 5p3. What would 5p3 include? I'm trying to count all of the different permutations of size 3 if I have a collection of size 5. And so it would be ABC, CBA, BAC, BCA, CAB, and CBA. All of these, when I do combinations instead of permutations, when I do combinations, all of these would collapse to just ABC. All of these in combinations, they're completely equal because they have the same 3 letters. And so here it was only 2, but here it's 1, 2, 3, 4, 5, 6 different ones. And so we included all permutations of the 3 letters that we picked. For combinations, we would have much less combinations since we would only count ABC as one combination, and all of these would be ignored because they're the same combination of letters. Then we would just go to ABD, ABE, BCD, BCE, and so on and so forth. And we would write it, I did the same mistake here.
Combination. Oh, 3C.
But it's the other way.
Combination 5.
It's
It's
the
the
one
next
next
one.
3P.
It's 5, 5C3.
Como picada.
No, yo la partí.
Nunca he probado la pitaya.
¿Qué es pitaya?
Grapefruit. Ah.
Okay, so Valeria's question was how, instead of having to write everything out, can we have an equation that'll just tell us how many different combinations we have? That's your equation. And you might notice that it's very, very similar. It's very similar to the other one, to the permutation ones. So this is NPR is equal, so with a P, it's n factorial divided by n minus r factorial. And with the C, NCR, is exactly the same thing, but at the end I have to multiply. In the denominator, I have to divide by r factorial.
Do we need to memorize that? The one on the right side?
The
Yes.
formula.
Yeah.
We have to know the formula too.
Both of them.
Yeah, you're numbers.
But what
It's
if
the same formula, you just have to add this at the end. Now, if you think about it, it makes sense. Remember here, ABC, ACB, BCA, BAC, BCA, CAB, and CBA. All 6 of these get collapsed into 1. And for each different combination, for each of these, previously I had 6 different permutations of that, and now I only have 1. So you have to divide by r factorial. The number that you're choosing, the smaller number, you have to divide by that factorial so that you can divide all of these 6 can collapse to 1, or all of these 2 can turn into 1.
The smaller number would be like 2 in spicy 2.
By C2, this is the smaller number.
You would put that in R.
And that's why you can see like these two just became 1, right? These 2 just became 1. These 2 just became 1. So I have to divide this, however long this is, I have to divide it by 2, right? To get this length. If every 2 becomes 1, I'm dividing by 2. Does that make sense? And so that's why the only difference is that I have an r factorial in the bottom. I'm dividing by something. The difference between my p, the size of the first list of the permutations, is this. Look, this is exactly the same, this part. But after I calculate this, I have to divide by r factorial. Now, in that case, r was equal to 2, and 2 factorial is just 2. So I am dividing by 2 at the end, which makes sense. But here, whenever I do 5 permute 3, I get 6 that disappear and just become 1. So I have to divide by 6, which is 3 factorial. I'm dividing by 3 factorial. So that makes sense. What was your question?
People who study a computer need to know this.
Computer science?
Uh-huh.
We take one class called discrete math, which goes like this and much harder. Much harder. I also took 2 math classes in college that were like, one was called proofs, and you just have to prove stuff, and the other one was statistics, which goes more into that as well. Because to figure out statistics, you need to figure out how many different options you have.
Do you think like your job surrounds around math?
Not so much, not computer science.
No?
No, not that much.
And like codes and stuff?
Huh?
Like coding?
Yeah, coding, you don't need that much math, typically. Like, not very advanced math. To prove stuff you do, but what, like day-to-day just coding stuff, you don't need that much math. No. Okay, so combinations are typically used, like your question might be, when do we use permutations and when do we use combinations? Well, you want to use combinations whenever you don't care about the ordering of your groups. A good example would be like in poker. Like whenever you're playing poker, if you have a poker hand, the same 5 cards, you don't care about the order that your cards are in. If you have the same 5 cards, it doesn't matter what order it's in, it's the same hand. Right? If you have a 2, 3, 4, 5, 6, that's the same thing as a 6, 5, 4, 3, 2. It's the same hand. Just because it's in a different order doesn't mean it's a different hand. And so you don't want to count all of the different orderings as different hands. You only want to count the unique combinations. And so we would use combinations whenever we don't care about the ordering. So for example, getting a royal flush is the same hand regardless of the order of the hands.
So it will be
order of the cards.
52C5.
Next slide. So, if we have a standard deck of 52 playing cards, the 52 playing cards have 4 different suits. So the 4 different suits, where's my red? The 4 different suits, the suits are just the symbol that they have. So we have 2 red ones, diamond and heart. And we have 2 black ones, which are spades, something like that, and clubs, which is like that. Okay? And we have 13 different cards in each suit because we have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. Those are the 13 different values, and these are the 4 different suits. And so the 52 cards are made by all the combinations of that. Now, question A asks, if the order of the cards doesn't matter, which we just said in poker never really does, how many different 5 card hands are possible? So what were you saying, Conan?
52C5.
52C5, right? Out of the 52 cards that are available, how many different combinations of 5 cards can I make? And so this would be equal to 52 factorial divided by 52 minus 5 factorial, which is the same as the 52p5, but then I have to also divide by 5 factorial.
Multiply.
I'm dividing, it's in the denominator.
But you don't multiply 52.
Well, this is a multiplication, but the multiplication is in the denominator. Like, okay, think about it this way. N factorial divided by n minus r factorial, right? This, and then I have this multiplication. This is equal to n factorial divided by n minus r factorial times 1 over r factorial. Right? This is the same thing. If I have this multiplication in the denominator, I can just split up that multiplication like this. But what is n factorial divided by n minus r factorial? What is this part? What is that equal to?
NPR.
NPR, right? So this is equal to NPR times 1 over r factorial, right? What is the definition of division? It's the reciprocal of multiplication. So if I do the reciprocal of this, I can switch this into a division. So that's NPR divided by r factorial. Right? So I'm dividing, and it makes sense that I'm dividing because the combinations will always be less. Because the permutations have all of the different like orderings for each combination, essentially. And so when I'm dividing, I'm getting rid of all of those different permutations for each combination. Okay, so there is another button on your calculator, it should be right next to the NPR that says NCR, and that's what the button is used for this. So it works exactly the same as the other button in your calculator. I'll do 52 and then press that button and 5. And I get 2,598,960 different unique hands. Right? Remember, I don't care about the ordering. I only care about the different distinguishable hands.
In the test, can we just do that? Like get it? If we show the formula.
To show work, I would really I only care about this actually. Like this is fun.
To put that in
We don't need to use the formula.
Right, I don't expect you to use this in the formula. You don't have to use it. Like, once you get this far, then you can just use the button in your
And where
calculator.
would you want to see us use the formula?
If I specifically ask you, but if it's some word problem like this, then you can do that. Okay, what about B? Read B. See what it's asking. First, I need you to understand what it's asking before we try to solve it. Do you understand what it's asking?
Yes.
So out of all of these 5 card hands, how many will have the same color? Now, notice it doesn't say the same suit. It says the same color. So you can have, as long as you have diamonds and hearts, that's valid. Or if you have clubs and spades, that's also valid. But you can't have a mix of red and black cards. Does that make sense? So all of the combinations of red and black cards, those are discarded, and we only want to keep all of the hands that are all red or all of the hands that are all black, right? Okay, so before we can solve part B here, we have to learn how to deal with multiple events. So whenever multiple things are happening, how do we calculate those combinations or permutations or whatever? So whenever you have multiple events, if you're trying to find the number of ways that both event A and event B, so just 2 separate events, if you're trying to find the number of ways that both events can occur, then you need to multiply. Typically, whenever you see the word and, it means that you want both of them to happen, okay? And so this is what we're going to need to do in part B, because we want to see like that we have a group of size 5 and also they're all the same color. When finding the number of ways that event A or event B happen, then you need to add your combinations, okay? And so depending, do you guys remember when we were going over the SAT problems that I said, like, whenever you see a word problem and you see the word like is, what do you have to write instead of is? Or like there were words.
Of is subtraction.
Of is multiplication, is
Addition.
equals, and then percent was divided by 100.
Product of is multiplication.
Divided by 100. Well, just of. Product means multiplication just by itself, but of was
Difference.
multiplication.
Subtraction.
Yeah. Okay? So in a similar way, here, whenever you see and, you have to multiply. We have to multiply your probabilities. And then in whenever you see or, you have to add them. Let's go back to here. In how many 5-card hands are all 5 cards of the same color? And so the first thing we need to do is see how many different ways we can pick a color. Because that's the first thing we have to specify. What color is it going to be? How many colors are available?
2.
2 colors, just red or black.
Red or black.
And how many do we have to pick?
26.
5.
No. How many colors
13.
for a hand before?
1.
Just one. Out of those 2 different colors, we have to pick one. So we have to do 2 combine 1. So this will be okay. How many different ways can I pick the color that I need? Which, I mean, I know it seems silly that we're writing it out, but
23.
it's whenever we have a different combination, this might be a little bit more difficult. Now, do you think this is an and or an or?
It's an or.
What?
An and because people can have all the numbers of the color, and some people could have different ones.
Well, essentially, I need to either multiply or add 2 things because I'm looking at 2 things. I want a card, a hand of 5 cards, but also I want them all to be the same color.
And
So I want both things to happen. I want the same color and also
different.
hand of 5 cards. So I want those 2 things. So I need to pick the color, and also now that I've picked the color, I have to multiply with what? If I already picked the color, how many different cards are available for that color?
13.
How many different cards are available?
26.
26. So let's say I picked red as an example.
26.
Let's say I picked red, just for example. So this, I already picked the color. It's either black or it's red, right? How many different cards, if let's say I picked red, how many different cards are there that are red?
26.
26. Half of the cards of the 52 cards, half of them are red and half of them are black. So,
28.
no, 52 divided by 2 is 26.
10.
So, once I pick the color, I'm only looking at all of the cards of that color, whatever color that is, red or black, I don't care. I only have 26 left. So out of those 26 cards that are available, how many do I want to combine? So I do 2 combine 1 times 26 combine 5. And I don't do 52 anymore because I don't have 52 available. I only have 26 to pick from, whatever color that is. So this equals, you can put it into your calculator.
131,560.
So 2 combine 1 times 26 combine 5. 131,560. So there are 131 out of the almost 2.6 million hands, only 131 would have the same color.
131,000.
131,000, sorry, yeah. 131,000. What if I wanted to find, so do you guys know the different hands in poker? What is it called when all of them have the same suit? All of them have the same suit.
Uniform.
So I have a pair, I have 3 of a kind. In English or Spanish? So there's one of them where all of your 5 cards have the same suit. Not the same color, but the same suit. Like all diamonds. So that's a escalera, that's a straight in English. So that's another one.
Royal flush.
So a royal flush is right. A royal flush is a special kind of flush, and so that's what I'm looking for. A flush is a hand where all of your 5 cards are the same suit. A royal flush is very specific. It has to be a flush, so all of them have to be the same suit, but also has to be a straight, which all your cards are in order, but also it has to be the best straight that there is, which is 10, Jack, Queen, King, Ace. So it has to be 10, Jack, King, Queen, Ace, and all of the same suit, which is really, really, really hard to get. So, how many different flush hands are there? How would that change from here to here? Remember, this is not a flush because it could have diamonds and hearts. A flush has to be either diamond or heart. How would that change?
2 groups instead of 5.
So let's do
One group out of one group.
C. We have to choose our suit first, right? That's what we did first. First we chose our color, but now we have to choose a suit. How many different suits are there?
2. 4.
We have 4 different suits.
But you gotta choose one.
1, 2, 3, 4. But we have to choose one. So we would have to do 4, combine 1. And then once we choose our suit, how many different cards have that suit? 13 instead of 26. So we would do 13. C5. What does that give you?
I don't know.
$5,148.
5,148. Okay. Now, these are all of the different flushes that are possible, and these are all of the different hands that are possible. So with these two numbers, we can figure out what is the probability that I can get a flush, like any flush basically whenever I get a hand. It is low probability, but what is it exactly?
5,000 out of
So I
2
can-
million.
5,148 divided by 2,598,960, and I multiply that by 100.
3.76.
3%.
¿Neta?
Where is it?
Uy.
You already did it?
No, pensé que tú lo habías sacado.
So 5,148 divided by
Te emocionaste.
2,598,960 times 100.
Según es mejor.
Basically 198. I'll round it up to 0.2.
Cerca, No, 2%.
0.2%.
Oh, no, I did multiply by 100. I did.
Uy, cerca, no.
So this is already in percentage. It's going to be really embarrassing if I got it wrong and if I did something wrong, but let's try to check it. Probability of flush with suited cards. Flubbing any one card flush, draw with an unsuited strip. No, this is more specific. No, this is like it's already taking into account the rules of Texas Hold'em. So yeah, I'll see if I don't want to keep doing this, but I'll see if I can find the actual just like
Mister, is 0.2% or 2%?
no
Point.
0.2% because I already multiplied by 100. So this was like 0.00198. I multiplied by 100 and I got 0.198. Approximately equal. Alright. I think that's good.